So thank you. Thank you first to the organization of this conference. I think it's a pleasure to be there and to have the opportunity to present the SEALIVE project research up now. So okay, I'm Amparo Verdú. I work at ITENE. ITENE is just give me to let you introduce a little bit of what we do in our research center. ITENE is a research center related to packaging, logistics, and transport materials. And we have more. I'm going to skip a little bit fast this part because I think we are a little bit late. But just to know you that we have more than 25 years of experience working on the packaging, logistics, and transport field, okay? And we work helping companies trying to develop or to improve their products. We work in different files in materials and technologies for the circular economy. We work in packaging, safety, design, and functionality. We also work in file of chemical exposure and environmental monitoring, and also logistics, transport, and mobility. So we work in the file of the materials, okay? We work along all the value chain. Starting, for example, coming from additives, modification, or making the functionalization of these additives, making the compounding, the formulation, the converting of these novel compounds, novel materials in real packaging, and also validation this packaging in terms of safety and also the transport, as I said. Okay. We also conduct self-life studies and active packaging to extend the self-life. We also work in inks in the development of different ink and labels for smart packaging, eco-design, and packaging certification. We just some numbers. We have different patents, and also we through the company builder Aspaka Ventures, we have founded 5 different startups, as you could see here at the bio, SafeLoad, Control Nano. And we are located in Valencia, in Spain. You are more than welcome to come to visit that. It's Valencia, so it's a nice city. And we are now expanding. As I said, we are a research center. We are lab and pilot scale capacity, but now we are expanding our facilities, but by building up an industrial pre-scaling for industrial pre-scaling project. Okay, trying to be more closer than the industry, and all the research that we perform achieves this TIRL to be ready to market, implemented there. Okay, this is our facilities. We have different additive modification and synthesis laboratory, pilot processing plants, transport simulation. So you will have all this information in the presentation. So let's go. Also, we are accredited, laboratories accredited for different testing services. And just numbers. Let's go through the topic of today, the SEALIVE project, okay? SEALIVE project was created, it was a project that was created to boost the use of biomaterials and also cutting-edge processing technologies to produce bioplastic marker solutions. Just let me give you a little bit of key information of the project. SEALIVE project deals with the strategies of circular economy and advanced bio-based solutions to keep our lands and also the sea alive from plastic contamination. This is a research project funded by Horizon 2020, and this is an innovation action. Okay, so we want to develop different prototypes, and also after you will later on you will see that we want to to test in real environment all these developments. The consortium is built up with 24 partners and plus 5 linked third parties, and we cover different locations in 13 different countries. At the beginning, it was a 40-month project duration, but after I think all the projects have been deal with this COVID situation, we need to make an extension of 6 months more, and not also for the COVID situation. I think it's also more related, as Chiara said. This is you're going to see that this is a very ambitious project with different 8 different demonstrators. So we have had a lot of work to perform. Okay, as you can see here, the overall objective of the SEALIVE project is to develop innovative and sustainable business models to bring to the market advanced bioplastics, biomaterial solutions by combining these new biopolymers by using new different sources, and also cutting-edge processing technologies for contributing to the circular economy. And you could see here the general overview of the project. As you could see here, the project, the SEALIVE project, is more or less organized in 3 different working lines. The more technical research working line, okay, developing these bio-based materials and so on. Also, as innovation action, developing these demonstrators and validating this demonstrator also in real conditions, and not losing the focus in the policy making, as Stephen commented before, trying to work with in this framework, in this policy making framework, trying to develop these new standards. Okay, as I said, SEALIVE project is a very ambitious project, and when we drafted the project, we tried to achieve as much as possible volume of different plastic materials that may cause the contamination, not only in land or not only in sea. So we merged together different demonstrators to achieve as much as possible. For example, we tried with 8 different demonstrators for land field demonstrators, and 4 more for sea applications. Okay, as you could see here, for sea applications, we have oyster mesh bag, fishing crate, fishing nets, the flexible deep frozen film. It's for fishing also applications. So as you could see there, normally the sea applications are related in textiles. For example, the fishing net or the oyster mesh bag, and also the fishing crate. And we tried to find the best end-of-life solution. And maybe we find out that there's no only one end-of-life solution to put it in each demonstrator. So for example, you could see here for the fishing crate, we set reusable, recyclable, and industrial compostable. All the demonstrators are developed with bio-based materials, compostable materials, okay? But for example, the fish crate, if we think in the end of life, the best end of life for this demonstrator is the reusability. So the fishermen, for example, with the fishing net or the oyster mesh bags, normally there are products that are reused with the analog fossil-based demonstrators are reused now in the market. So we try to replicate this reusing end of life. But if, for example, we are using in the sea the fishing nets, and there's a problem, and this fishing net is going to be in the sea, we need to assure that this fishing net is going to be, for example, marine degradable. This is, for example, the oyster mesh bag results that presented Steven before. So for the land application, we cover different packaging, food packaging or food containing, also agricultural films that we have mentioned in other projects before, and the single-use cutlery. And okay, as I said before, this is an innovation action, okay? So we wanted not to keep the results of the biodegradability or the compostability or aging, for example, at lab or pilot scale. So we are going to perform now, we are maybe on the last part of the project. It remains more or less 1 year. So now they are going to start the real condition trials. So for example, the sea application demonstrators are going to be tested in real conditions in, for example, different sea environments. Fishing nets evaluation is going to be performed in the sea, the Cyprus Sea. We are going to test also the fishing boxes. The oyster mesh bags are already been tested in, I think it's the Mediterranean Sea, in the part of the France also. So, as I want to remark in this, so this innovation action is trying to achieve this development in a real closer, the most closer to the market possible. I have here a short video, but I talked to Chiara, and I think it's the best option is to skip it because it's going to change the window, and maybe I crash all the. So I think if you are going to have available the presentation, you can go through the short video, and this short video is the people, the fishermen of the Cyprus are still working with these development nets, the SEALIVE development nets. So you could see how these fishing nets works in real environment. Okay. So today I want to go a little bit deeper for the sorting technologies, okay? The problem of the sorting for biomaterials, okay? We have now near options for sorting biopolymer materials, but the problem is that we can, with these near technologies, we can make the sorting of 100% raw material. So, for example, 100% PLA is able to be detected in the sorting equipments, but normally you are going to find in the market, you are not going to find 100% PLA products. Normally, in order to improve this thermal stability or these mechanical properties, you are going to find in the market blends, additivated materials. So that's the problem. This identification problem in the sorting equipment that we have today available in the market, we wanted, or we with this SEALIVE strategy, we wanted to tackle this by using organic pigments that have been founded to have different fluorescent response. Okay, so inspired in other different research that we have been carried out, we found that chlorophyll, for example, chlorophyll extract from chlorella algae, where if we are able to encapsulate this material to process it, we can be able to put in bulk in the material, in the bioplastic material, and this fluorescence response is not going to be lost. So in order, the strategy that we have performed with the project is to use this layered double hydroxides, LDH, okay, to encapsulate these organic components to avoid thermal this thermal degradation during the processing. And also we have to take in mind that it's not the first processing step that we need to be able to pass. If we want this material to be recyclable and to be sorted in this equipment, we need to be able to reprocess different times the biopolymer. Okay, so the encapsulation and the compounding step, we could see here some pictures for the different steps, okay? First step was these natural pigments. We used two different, chlorophyll and also carotenoids, were extracted in ethanol from Chlorella algae, dry biomass, and the pigment extract was added in the hydrated nanoclay and stirred. The second step was isolated and making the centrifugation of this sample, and the encapsulation yield of the natural pigment in the LDH was determined by UV spectroscopy. Sorry, and it shows to be above 90%. So it's a very good response. The clay was compounded also in with different biopolymers. We see later on at laboratory twin screw extruder, and after that injected into dog bone specimens. So we have processed it in two steps: compounding step, also injection step. And after that, you could see here that fluorescent biocomponents, biocomposite specimens, you could see here this different UV response, the fluorescent response, with different also percentages of the maker, from 0.25 up to 4%, okay? We use it as a polymer matrix, different matrices, okay? As we have said, we have tested with PLA, raw PLA, 100% PLA, but we use it also a blend of PBSA and thermoplastic starch, okay? And as you could see here, in all the cases, we can be able to detect this fluorescent response. Sorry, but you could see here the processing temperature. So we will be able to process and not to degrade these organic pigments, processing the materials at 190%. And after that, we reprocess it 3 times, up to 3 times the materials. And after the third reprocessing cycle, we still, okay, the response is not the same. It's not as bright as the same, but we still be able to show fluorescence response. So it seems that we'll be able to go to mechanical recycling, and after that go through another product and another cycle of sorting. It's going to be able. So this is the research as I can see you or show you up to now. But as I say, we are now in the final line of the project, and we will be able maybe in 6-7 months to show you more information. So I invite you to find more information or to contact us to more information. Just 6 months later. Thank you.
Thank you, Amparo, for this nice introduction on this project. I did not realize that it was 1 year left for you for doing all so
more or less.
You got 1 hour. Some people here have got 1 month. You got 1 year, so very nice.
But there are a lot of demonstrators, so it's quite difficult to try to achieve as much closer position to the market with so much demonstrators.
Yes,
so
for the
this is a point for new projects.
Reduce the demonstrators.
Yeah.
The nice tip. Yes.
Yeah.
I was wondering if I may I go just, I have one question. I wanted to check with you, how did you deal with standardization activity? Because I saw a number of SEN committees, and have you been working with them directly or indirectly to some of the partners? How do you feed into standardization?
Normally, I think Stephen also can answer more or less the question, but we are different 25 partners, okay? And we belong also to different research centers or organizations. So we are also involved in different committees, standardization committees. We are also partners that have directly in touch with European Commission and the directives and so on. So I think,
I think I give the word to Cristina, and then we go back maybe to standardization.
Okay.
Hi, Amparo.
Hi.
Thanks for your presentation. It's very interesting. I could see that you could see the fluorescence signature after 3 reprocessing.
Yeah.
And my question is regarding if you have been comparing this to NER somehow, or how are the advantages against NER, and what would you say? Because in our case, we were working in these tracers with NER, not fluorescence, and in textiles, and it's quite interesting research.
The point to use these fluorescent makers, because in the project we have tested all different sorting working lines. For example, for the fishing crates, we use RFID tags also. But the idea of these fluorescent makers, I think the best advantage is in the mix of a final product. As I said, for example, NER options are perfectly implemented. We have also a partner in the consortium, Pellenc, that has implemented the NER option in their equipment, and PLA is perfectly detected, but 100 PLA material.
Yeah.
And as I said, we are not going to find the big amount of packaging or products that we are going to find in the market. They are not going to be 100% or raw PLA. So I think the advantage is that we can put it in bulk when we are making the blending, the compounding, and we can find, for example, blend, as I show you, a PDSA TPS blend, and reprocess, and we can sort also with these fluorescent makers. And also the carrier that we have used is a nano clay. So for textiles, it doesn't be a problem.
So one more question from me as well. So first of all, thank you for the interesting presentation. So I was wondering also regarding the fluorescent markers, if you see any color change in the material, also just visually. So
but you means without this UV light?
Yes. So for example, if you would make a white yarn or a white piece of plastic, if you would see a yellow or a green shades with these.
Normally, because the amount of the material, it's not so high. The percentage, for example, with 0.25%, we also are able to show this fluorescent response. And also we are using nano clay carrier. Okay, so if you work, you need to perfectly make the dispersion in the compounding step of the material. If you have the agglomerates, you are going maybe to be a little bit change of the color, okay, in the raw material. But if you are the material is well dispersed in the compounding steps, there's not going to be any problem. You only will see this change of color with this UV light.
All right. Okay. Thank you very much.
Yeah, thank you for the kind introduction. And also thank you for inviting us to be here to present our NENU2PHAR project, which aims the production of polydorsialcanoates from microalgae as feedstock, and the use of this biopolymer to produce high-volume consumer products. But yeah, before presenting our project, please let me to very briefly introduce my company. I work at LOMARTOV, which is an environmental engineering and consultant company in Spain, in Valencia, in the East Coast. We are an SME, a very young SME, as we were founded in 2017. And we are very active in EU-funded projects. Indeed, around 80% of our incomes come from these European projects. And we have mainly two lines of activity. The first one, which we call Innova. And what we do here is to support companies and organizations to develop their ideas from the beginning up to reach the market. So we provide support in terms of technological coaching. We look for financial support to develop the projects and these ideas. And we also provide support in issues like certification, standardization, regulatory compliance, and all the aspects related to business development, exploitation, and IPR. And the other activity line of the company, which is called Sustainable Solutions. And what we do here is to basically apply life cycle sustainability assessment tools to measure and improve the sustainability of new products, processes, or technologies. And we also apply eco-design to improve the environmental performance of these products or processes. And this is just the role we are playing in the NENU2PHAR project. We are using life cycle assessment to validate the environmental, economic, and social sustainability of the new materials and products we are developing with the PHA. And we are also supporting the industrial partners to implement eco-design systematically in their products. So, and moving now to the project, these are the contents of the presentation. I will first provide some key figures on the project, then I will present the main objectives, the project concept, some progresses achieved to date, and finally I will conclude with the benefits that the project can bring. So our NENU2PHAR projects, I mentioned, is aimed at develop sustainable PHA-based materials for high-volume consumer products. It is a Horizon 2020 project under BBI program. It has a project duration of 42 months, so we are now in our last project year. And we have 5 million euros contribution from the European Union. The consortium is made of 16 partners, including some research and technology organizations like our coordinator, which is CEA from France, but we also have some other centers like ITENE or SEALIVE, which are also today here. It's good to see them here today. Or IPC, and then we have several companies, both large industrials and SMEs, which are mainly, some of them are mainly involved as end users or for validation of the developed materials in final market applications. And we also have an innovation cluster to ensure the transferability and engagement of the stakeholders in our project. The objective of the project is to develop new competitive PHA polymers from the microalgae. So this is the key objective, but then we are also addressing the improvement of the properties of these polymers by means of compounding to reach different target applications. And we are also testing the performance of these polymers in different processes linked to these different market applications. We are also implementing eco-design in the PHA products, targeting different market segments and going beyond the use of the PHA material, but also addressing the improvements in different life cycle stages. And also another objective of our project is to demonstrate the circular economy and sustainability of this new PHA value chain. So we are conducting shorting and recyclability testing, and also biodegradability testing to be sure that we are able to close the loop with these materials. And we are applying a life cycle sustainability assessment to be sure that our proposal, the materials and the products we are developing in the project are more sustainable than their current counterparts. And finally, it is also our objective to increase the stakeholders and consumer awareness. This is why we are today here to do so. And for instance, last month we organized a workshop in France to discuss about social acceptability of these bio-based materials and products with relevant players. The project concept is covering the whole value chain of the PHA-based materials, from the microalgae to the production of final applications in different market segments. So we started with the microalgae. We tested different algae species to select those that provide higher yields in terms of PHA production. We cultivated these algae using different photobioreactors technologies. And then once the microalgae biomass is harvested, we also tested different technologies for cell disruption and extraction of the starch. This starch is further used in bacterial fermentation to obtain the PHA, which also needs extraction and purification processes. And again, we tested here different process alternatives. And finally, once we reach the PHA, we formulate and compounding it to and process to reach the final applications. In our project, we are demonstrating the applicability of these materials in 9 different demonstration products, which cover 5 market segments, including food packaging. We develop different types of food packaging like films, pouches, cups, and trays. We are also producing cosmetic packaging, a roll-on bottle for cosmetics. We are also using the PHA materials in 3D printing filament. And finally, we have 2 different textile applications. One aimed at the medical sector. We are producing surgical niches, and an agro-textile for landscaping. And with this project, what we are doing is to move towards 3rd generation feedstock for the production of the PHA. So we are using the microalgae as the feedstock, which avoids all the controversy related to the 1st generation biomass, as we do not compete with the food. We avoid this controversial issue. And we are not using agricultural land in any case, so we prevent environmental impacts that might arise from agricultural practices. And then the other advantage of the project concept is related to the end of life, to the biodegradability of the polydoxyalkanoates. We are producing some different polymers, but PHB, for instance. And as you can find here, and as you know, they have biodegradability in many different environments, like obviously industrial composting, but also home composting or soil or even aqueous environments. And this might be really interesting for some specific applications. For instance, for the agro-textile, the soil biodegradability is really It's a really interesting property, but also for some other specific packaging applications, the home composting could be an interesting alternative and it is interesting for our industrial partners for some market niches. So in the project, we are testing the biodegradability of the different PHA-based compounds and blends we develop for different applications. And at the moment, we have quite good results, very positive results, even though the tests are still ongoing. And okay, at this moment, we have been already able to produce PHA from the microalgae. We were able to cover this whole production chain and select those technologies at each process step that better work, but we are still trying to improve the yields at each process step. So these figures you can find here are not totally updated as we are still working on it. But what I would like to show is that we were able to obtain this PHA, 1 kilogram of polyhydroxyalkanoate using almost 6 kilograms of microalgae as the feedstock, which allow us to capture 11 kilograms of carbon dioxide. Well, at the moment we have used CO2 from bales, but this opened the door in the future to have this technology as a carbon capture and use technology, which will allow it to benefit from economic incentives and this kind of incentives of this kind of technologies. So it's something good to make the production chain even more profitable and economically feasible. And as I mentioned before, we are also implementing eco-design in the different demonstration products in our project. We supported the industrial partners developing these products in the implementation of the eco-design systematically. And one of the steps we conducted for this purpose was to do the LCA of the current products. This is an example for a rigid food packaging film, and this is the carbon footprint of the film for the whole life cycle. And what you can find here is that over 60% of the carbon footprint is due to the materials used. In this case, the fossil-based plastics. So it seems that the replacement of the fossil-based plastic with the PHA could be a really interesting solution, provided that we are able to make this PHA more sustainable from the cradle to the gate. And this is something we are checking with the LCA study in our project. But we didn't stop here in the materials, and through this eco-design procedure, we go beyond the use of the PHA in the products, and we also propose other eco-design measures for the different life cycle stages of the product. So for the 9 different products, we consider different measures, for instance, reduction of material usage. For some products, we also propose alternatives to improve the manufacturing of the products, or even alternatives to improve the end of life in terms of recyclability. For instance, for the bioplastic products, we propose measures to redesign the products to be sure that once these bioplastic products reach economies of scale, they can be really recycled. And some of these measures will be implemented in the prototypes that are produced in the project and validated by means of this life cycle assessment. So to conclude, the benefits that we expect to obtain with our projects is obviously to reduce the dependence on fossil resources, as we are using this microalgae as a feedstock to produce the bio-based PHA. This can also reduce greenhouse gas emissions, as we are reducing the CO2 as to feed the microalgae. And as I mentioned before, there are here some opportunities to use industrial flue gases and have some economic benefits from CO2 allowances. Then we have these benefits to increase social acceptance by avoiding the controversy of the competition with food production or the environmental impacts from agricultural practices, as we are using a third-generation biomass. which can also be interesting to support the local bio-based economies in Europe, as we can have new algae and bacterial biomass farmers. And finally, we have an alternative end of life in case these products are incinerated with energy recovery. At least this would be, let's say, neutral in carbon, as we are emitting biogenic CO2. But then we have this alternative end of life scenarios related to the biodegradability, like the home composting or biodegradation in other environments like soil or water. And finally, our aim with this project is to provide another step towards the take of the bio-based materials in high volume consumer products. And that's all from my side. If you have any question, I will be related to answer. Thank you.
Thank you for the invitation to Recover project. I would like to start to apologize on behalf of Maria José López, is the coordinator of this project, and she couldn't be able today to attend this conference. So this is Macarena Jurado from University of Almeria. I'm part of the research group of Maria José López. So I will try to share with you some of the context of the Recover project, some of the solutions that we proposed, and some of also the products that are obtaining right now to finalize with the expected impacts of this project. Well, Recover project is of 4 years project. It started in the middle of the pandemic, in the beginning of the summer of 2020. There are 17 partners involved from 7 different countries, and we have a budget of 5.8 million euros. And I would like to highlight 2 singularities of the Recover project related with the topic of the call, where it was granted. One of them is the basic tools. We are using not only microorganisms or enzymes, but also microorganisms and their enzymes, even novel enzymes and insects, earthworms. This is something that I would like to stand out. And on the other hand, related with the target, the plastic target, we are focused on plastic for food packaging and plastics derived from agricultural systems. Related also with the partners. We are the coordinator of the University of Almeria, of course, is the coordinator of the project, and there are 4 more universities in the consortium of Recover project, 1 association, 1 non-governmental organization, 7 MEs, and 3 large enterprise also. And we have experts from different aspects. We have waste management, insect culture, different research, diverse group of partner here. Following with the target, with the plastic target, we are working with agri-food waste plastics that are generated at the end of the life of almost 0.5% of worldwide production of plastics that are derived from food packaging and agriculture, so are big numbers. Some of these waste generated during this, at the end of these processes, are finalizing on the soil, contaminating soils directly. If we are lucky, some of them can be collected and take to waste management systems. And in these systems, in these treatment plants, there are a number, I'm sorry, I cannot see this. Okay, my screen was a little bit occupied, sorry. Some of the plastics in the European Union, we are lucky also because we have 31% more or less of recycling plastic, but there are another part of the world that are worse. But this is not enough, of course. The majority of these plastics are non-recyclable. Some partners, some colleagues, sorry, in this conference say before, speak about this. They are mixed or multilaminated, so cannot be recycled. and the destiny is incineration or disposal in landfills. This is a big concern. And on the other hand, what happened with the organic fractions in waste management systems is that most of the time is mixed with plastics. So although in the treatment plants, they are trying to compost this organic fraction, composting, the compost, the final product is contaminated, so it cannot be used like an organic amendment in agriculture. So Recover is trying to do some solutions for this situation by bioremediation of compost and soil contaminated with plastic, and also looking for new biorecycling routes. This is a graphical abstract about the project. We can see our plastic target and our biological cocktail, our solution, that include microorganisms, enzymes, insects, and earthworms. There are different routes because there are different approaches. Some of them are related with ex situ treatment and another with in situ treatment I mentioned later. At the end, we are looking for valuable solutions. So we want to eliminate the plastics, of course, non-biodegradable plastics, but we also need to take another product, bio-based product. This is from insect exoskeleton, and also we can obtain biofertilizers during the processes of all of these projects. Recover solutions then have like 5 points different. At the beginning of the project, we were, some of the partners were quantifying, characterizing, defining, collecting the plastic target that was the raw material for our project. Some of them in municipal solid waste because they come from food packaging, from citizens, and not only from companies, and from compost contaminated agricultural plastics and so on, as I mentioned before. In parallel, another part of the partners, I am in the microbiology team, of course. We were selecting, isolating microorganisms, looking for the best solution, the best combination between insect, earthworms, enzymes, microorganisms, and looking for a specific solution for all of the specific situations that I mentioned. In fact, we have this in situ bioremediation of soils, this first problem that I say before, ex situ bioremediation of compost and vermicompost, and also this ex situ treatment related with insects and related also with non-recyclable plastics that I mentioned in the slides before. So we are right now in this part, in this point, we are upscaling and monitoring the presence of this combination, especially microorganisms. We need to know if they follow, they are working there in these samples, and also we are checking the biodegradation capabilities of all of these cocktail biotech solutions. Also, we are working right now in the developing of added value byproducts, improved biofertilizers, and chitin-based biopolymers, new bio-based products. In our transversal way, of course, we are working always, we are thinking always in the environmental and economical impact of these treatments. Really fast, I would like to say something more, a little deep of the type of target plastics. Of course, we select this plastic because of the data, the number of production of this type of plastic, food packaging and agriculture, but there are a lot of types of potential plastics, but we choose some of them that was with potential biodegradation, really difficult, of course, but I mean LDPE, LLDPE, PS, and PET. This was our target plastics. The tools are complex because we have endoplastic microbial consortia. Endo, I mean, they are from the gut microbiota of the different type of earthworms. You see the different type of insects selected, And also we work with EXO-PMC, plastic microbial consortia, that are from the collection of our research group and from different environments. So we have, as I mentioned before, also the a solution specific for each type of treatment. As I say, we are upscaling and monitoring nowadays. This is Steven and another partner of the project are here today in the conference. They are monitoring the biodegradation of capabilities of this cocktail. There are another partner of the project doing this right now. So this is currently running, it's ongoing. I would like to mention the value of this extraction process. This is also Patrizia Cinelli of Univ in the conference, I think. They are trying to obtain different formats of new bio-based products like pots, packaging, films, containers, coated films, and it comes from the cocktail that contain insects. When the insects do their job, they trying to biodegrade the plastics. We can use the exoskeleton to do an extraction process, green process, because we are always thinking, of course, in sustainability. And with this chitin, we can convert to chitosan, and with this chitosan is produced all the bio-based products. This is some pictures of how it's obtained with this biomass of the insects. Is doing a process of demineralization, deproteination to obtain chitin. This is made by a university there in Germany, ASU, also another of the partner of the project. And this chitin can be converted to chitosan by the acetylation. This is some micrographies from Univ comparing chitin and chitosan obtained by ASU and with some commercial products. And I would like to show you, this is also by Univ, some of the films, some of the products that they are obtaining with the value added to be antimicrobial and antioxidant, to have these properties, as in another project was mentioned. I think polybioskin, really interesting also. These properties are really good because if we are trying to substitute this food packaging for another biodegradable or more biodegradable type of packaging, and also we can be more conservative with food and being antimicrobial, antioxidant. So this is good news, of course. The other value product is biofertilizers. Biofertilizer can be obtaining on one hand from insect frass. We have convert the exoskeleton of insect into this chitin and chitosan. But what happened with frass? Well, it has good properties as biofertilizers. And on the other hand, vermicompost, where some of the earthworms were acting, of course, with the help of microbes, like always. They are obtaining in the University Miguel Hernandez, in fact, on another of the partners, they are obtaining different formats with different additivation of biofertilizers. And in fact, we are collecting data about that, also about the microbial profile of these biofertilizers, and the results are being really good. Spoiler, will be soon. This type of results. Just I would like to mention also the implementation of the recover model based on all the information that recover. Some of the partners are receiving of different stakeholders, and also the scientific knowledge and technology knowledge that recover is generating. It is helping to maybe in a near future could do a model of recovery project in a large scale. And just to finish, I would like to conclude that recovery is make a contribution to the bioeconomy, in the sense that we are establishing new circular cross-sectorial interconnection, especially waste management and biotechnology. we are creating new effective bio-based value chains. But not only this, we are also contributing with the environmental sustainability, because we are trying to reduce, this is what we are expecting in the near future, reduce the generation of microplastics dispersed in soils, in compost, vermicompost, and increasing plastic recycling up to 12% in European Union, providing new alternatives for removal of non-biodegradable plastics on soils, compost, vermicompost, and of course, avoiding around 80% of CO2 emissions caused mainly by the incineration of this plastic that nowadays cannot be used in other way. So you have here the contact details, of course, myself, but coordinator of the project, Maria Jose Lopez, who could give you more details about this project. And thank you very much.
So, okay. So thanks for this invitation and for this opportunity to present our project ECOFUNCO that was just concluded in July of 2022. And is a project about eco-sustainable bio-based coating with several functionality to improve the performance of packaging and healthcare products. And also we investigated sustainable end-of-life options for this material. The project is based on the valorization of biomasses, and so interconnects with all the other projects we have presented up to now. And it was the follow-up of several previous projects we have made as ISTM and UNIP. Some of these were already presented, such as polybio-skin, recovery is running now, and many others we did in the past on the use of protein for barrier to oxygen, biomass valorization, as in agromats, kitting use, and so on. So these were all projects where ISTM and UNIP, which are also present with some of our professors in this meeting. ECOFUNCO project was joining 17 partners from different European countries and even participation of Turkey and Israel. It was merging, as usual, researcher and industry. I have to say that even the industry were really active and participated strongly to this project. I know that some of them are also present there, such as Aris, Alka, and Biomi, and several. It was a very nice project with a very nice cooperative environment. The aim of the project was to valorize agro-food waste and byproducts, and basing even on the activity performed in previous projects. One line was on the extraction and use of chitin and chitosan, mainly for their antimicrobial properties. The extraction and use of cutin, in this case, applied as coating on plastic and paper, while, for example, an agromats project was coated on metals. Proteins from legumes, and other functional molecules, such as some antioxidant or other molecules, which were as well extracted from tomato skin, melon seeds, other types of legumes and seeds, all byproducts, never main food, but always remaining a discarded part of the main food production chain. Application were in healthcare and personal care, disposable products such as the tableware, and packaging. So make also multi-layer packaging, but where all the components were biodegradable, compostable, or anyway recyclable. So why this? Because the market of packaging is huge, and both in cosmetic, healthcare, packaging, tissue, very often they use multi-layer material. This multi-layer material, especially when match plastic, paper, and metals, are very hard to be separated and to be recycled. So they often go to landfill or incineration. While the single material valuable for recycling, or if we make a proper combination, as we did in ECOFUNCO, they proved to be even compostable or soil biodegradable, depending, of course, from the plastic substrate. I report some of the previous paper we did where you can find some of the speakers of today, like Professor Lazzari, Professor Coltelli, and Dr. Braca. So according to many studies, there is a huge waste of food, and this is really not acceptable, not only from an economic, but even from an ethic point of view. And then, you know, that production of food is polluting. So wasting food is bad from any aspect. So improving the shelf life, improving giving to packaging antioxidant, antimicrobial properties is very important, and is still envisaged also in the new topics of the European Community proposal. So one main part of the ECOFUNCO project was the development of packaging with good barrier. We had the Consorzio Prosciutto di Parma as a member, so interest from sliced ham, sliced cheese, and even interest for perishable but high value products to increase their shelf life, as well as our paper producer, large company partners, Organic Chimia Otamaki, had a huge interest in the paper-based tableware. But as you know, the plastic tableware is had to change to biodegradable raw material, and this was not so easy. At the same time, even in cosmetic and healthcare, having tissue which are degradable will save us from the problem of microfibers and nanofibers in the environment, because the cellulose, chitin, and other types of fiber will naturally degrade in the environment. So different targets. The targets were to achieve good enough barrier to liquid or to gas for food packaging, or antimicrobial, antioxidant properties when we go to cosmetic and healthcare properties. The third part of the project was to identify reliable provider, giving the biomass, and use the biomass in the partner who were more involved in the extraction, and try even to apply in the project green chemistry, biotechnology approach for extraction, which can make our material more sustainable, because being the products interesting, biobased, and efficient, sometimes the extraction may not be so green, as in case of heating and transformation to ketone. So we made also a parallel research even to improve the sustainability of the functional molecules and the raw material that we are going to use in the project. All the biomass are available even in Europe. Of course, they are available worldwide. And as I said, they are byproducts and waste products of the agro-food industry. So no food competition, no competition with the main line of production of this raw biomass. The first part of the activity was developed mainly by Fraunhofer, by University of Sheffield, and University of Alicante, and SICA, there is a technology center in Parma, which started, as I said before, the extraction of the main raw materials, so the protein, the coating, and the ketene, trying even innovative approach. And they already published some of the first results, and some more papers are still under writing, because, as I said, the project just finished end of July, and several scientific papers were slowed down by patent application, and as you know, with the company consideration what has to be exploited and what can be exploited even with publication. Especially Sheffield worked a lot on production of polydioxycanoates and bacterial cellulose, Parma in Italy on the coating production, while Germany on the protein production, and Alicante on the extraction of chitin and chitosan, and even the support in the extraction of coating, not only from tomato, but even from melon seeds, using even supercritical carbon dioxide, microwave assisted extraction. So different types of innovative process. Most of these results are already published, and some were protected in a patent by a university of Alicante. And the polydioxyalkanoate produced were also tested to coat on paper and plastic by wet coating and by electrospinning. One advancement very important was made in the structure of coating that was already started in the Agimas project and brought to a spin-off company, Toma Paint Company, near to Mantova. And in this in the project, University of Alicante developed greener process for structure, which, as I said, has protected the food by a patent and then published partly in a paper. We were using a technology going to have a lower environmental impact. So technology reducing the use of chemical, achieving quite a good yield of the structure. And this coating was used in the project to be applied as a coating. As I said before, this was a kind of follow-up of a very successful example of Agimas project, bringing to a plant near to Mantova, and this company, which is still active and growing very well, coming from the activity of Sika and Chiesa company in Mantova, going to this spin-off, who is a provider of coating even for us in these and other projects. For the use of chitin and chitosan, this has already been introduced. Even here, we say we had worked in previous project, nanoketopack polyvioskin, and chitin can be extracted from many different sources. In this project, the chitin was the traditional one from shrimps and crustaceans, while in our project, we're also trying from insects and from fungi. Nanochitin fibres in particular, which here were produced by SEALIVE, a company in Belgium, are very active, extremely active as antimicrobial. And we applied the chitin on tissue paper and on plastic paper. Some of these results were already published by our group together with Alicante and SEALIVE, as in the cited paper here reported. This is, of course, a nice contribution to the bioeconomy because of this coating, chitin, and I would also even protein applied on substrate can give us valuable products which were developed both from polysaccharide, cellulose substrate, and plastic substrate, and depending from the substrate, propose for really many different types of application. Improving the economy of company like SEALIVE and all the plastic producer company in our project, like Branded Bioplastics that is present in your meeting, BioMe, TIPA, and the paper producer company such as Utamaki Organic Chemia. So we developed the demonstrator in plastic, paper, and cardboard, and tested and validated them for application with the slice ham, slice seeds, containing liquids, food contact, migration, antimicrobial properties, and finally, our partner ARCA Laboratories, who is also present in your meeting, tested the compostability, the durability in soil, and sustainability through life cycle assessment. Some example of material coated on plastic and paper were made in laboratory scale first with spraying technology or application with a knife coater, and by industry first in laboratory scale and then in pilot and industrial scale. So we made the coating with a single material, coating, chitin, or protein, or matching them, coating protein, chitin protein, 3 of them, 2 of them, depending. Because of course, if I have an open glass for water, I don't care barrier to oxygen because it's open, but I care barrier to liquid. So depending from the application, we were using 1, 2, or all the 3 coating coupled together. Using protein from lupine, the coating from tomato and melon seeds, and the chitin, especially the nano chitin provided by SEALIVE, and then assembling of the multi-layers, that is a work performed together with industrial partner and Fraunhofer Institute in Freising. And SEALIVE improved and developed the production of the nano chitin solution to be applied both keating from mushroom and shrimp. We went more on with rest of shrimps because we had more experience, but that's where made even with keating from mushrooms. And the three companies divided the activity. So TENEU2PHAR worked more on coating, while the Planet Bioplastic worked a lot on keating and hot melt coatings. BioMe worked more on wet coating, and we cooperated with a Spanish company, Condensa Química, to give us additive to improve the fluid solution to be applied in the wet coating and the property of the hot melt coating. All the materials were regularly tested for barrier to oxygen, barrier to moisture by Fraunhofer, and microbial antioxidant activity by Iris and our partner. It's evidencing that the coated material with keating, nano keating, had really an effect, were really efficient, especially versus systemic coli and Bacterosaurus. And we isolated the combination which we are most performing, which had several, of course, and we then isolated those formulations for the scale-up, for the demonstrator, and for the final validation. Some activity was made, as I told, on hot melt, which was developed in the University of Pisa and scaled up by Planet Bioplastic, and we also applied for a patent on this technology. And so this material can be applied by coating, by melting, using low melting polymers. So different types, even here, we develop different types of formulation and combination of polymer, plasticizer, and nanokeating or chitosan. And also this film were able to be produced in industrial scale and to be validated as good film for barrier and antimicrobial properties. And different companies developed the scale-up and prototypes production, which was made on paper and cardboard substrate and plastic substrate, because we developed both demonstrator based on paper and plastic, all different layers of plastic, depending from the requested application. But even in the case of paper and plastic, the plastic was biodegradable, so compatible with paper. And the test made in Science Center in Lucca confirmed the maintaining of the recyclability of the paper together with the biodegradability. Iris' role was to develop a system to monitor the coating, which was applied in Fraunhofer Institute machinery to control the thickness and the quality of the coating during the processes. So being in advanced technology and combining control of the process to the technology developed. These are some results of the developed material produced in industrial scale, which confirmed what was seen previously in the laboratory scale, and some of the most performing material who confirmed to be valuable both as antimicrobial than for mechanical properties. So depending from the substrate provided by our industrial partner, some film were better for flexible or thermoforming, depending, of course, from the substrate provided, since the coating would not to be changing significantly the mechanical properties, while giving the barrier and the antimicrobial properties. These are an example of a hot melt coating applied on paper in organic chemia. Some example, the demonstrator made in laboratory home scale, but this was because we wished to make one test of the species, and one test even of the packaging and the antimicrobial antioxidant activity. And we evidenced excellent water release barrier properties, and these materials were really satisfying even the demand of the company. Tissue paper was treated And in tissue paper, we had to work a lot on the method to apply the coating, not to destroy the tissue paper. Anyway, when we finally set a nice method, we could verify nice antioxidant activity with the polyphenols that the University of Alicante had extracted from tomato or melon or our agri-food biomasses.
Patrizia, we need to wrap up.
Yes, these are the last slide. So these are some examples of the demonstrator which were tested and proved to be efficient to pack the slice hand, maintaining the organoleptic properties. And we ran the test up to 30, 60, and 90 days. As well, the degradation test made by ARCA proved that the coating is not hindering biodegradability and compostability, both as mineralization than as toxicity in plant. And sustainability study evidenced that we can achieve some saving in carbon dioxide emission, especially in the carbon paper, and the cost can be made a reasonable and interesting cost for the market. So industry were quite happy. So we have come, I already summarized. I just want to finish with the challenge to say nothing is perfect. We still have work to be done. To protein coatings needs a little bit to be improved. Coating is colored, has an odor, is sticky, so we got great results, but not yet to industrialize. We want to scale up and to go on. The scale up of the hot mess with coating was very challenging, but we arrived to good results. And adhesion between plastic substrate not always was perfect, so even here we needed to research on adhesive, and we hope in an ECOFUNCO too. So let's see if we can get one. So challenge can be as well the cost, the reliable deliverable of biomass, get the consumer acceptance in new product, adapt the production chain. And I just close thanking all the partners of ECOFUNCO project. A lot of them are present in your meeting, and inviting you to the conference we're organizing at the end of June in Pisa, where we also would like to make a networking among partners in bio-based material, which will be 28 to 30 June at Le Benedettine in Pisa, hosted by University of Pisa. And you are very, very welcome to send a contribute here.
Thank you, Patrizia. It was very exhaustive. And I think this is also a very nice opportunity that you're giving to other people to connect to your team, consortia, maybe upcoming consortia for ECOFUNCO too. So good luck. Any question to Patrizia? I don't see questions here. I do not see anyone tipping on the chat. So I think we can wrap this up. I will ask you to stop sharing the screen. And my idea was actually to reclaim the host role. Yes, excellent. Okay, so we are at the end of this conference.
Chiara, I think there is a question in the chat now.
Okay, no, it's not too late.
Okay.
Can you read it from the chat?
Yes. Do you use a substrate purely made of cellulose and coat chitin on it? Do I read it correctly, the question, Docs?
We use different types of substrate which were provided by the paper producer. And yes, most of them were not coated cellulose, were normal cardboard or paper substrate. Some other had some coating of clays, but most of the, especially the first one we did, were just raw cardboard or paper substrate, changing just in grammage.
I just wanted to give you a very quick introduction on something that is coming up and that maybe you're not aware of. So we'll skip everything that is related to statistics and so on. And I would like you to focus on this message. This is like something that is coming up internationally binding for all of us in different countries, and will be actually demanding national governments in 175 countries to fight pollution together. So I see different projects going in different directions here, but the common thread here is actually the pollution fight, the reduction of the emissions, and in general, the use of bio-based material instead of fossil-based materials. So there is this discussion related to a treaty, a global treaty at UN level that is taking place. It's already in the second round. And this treaty will become binding by the end of 2024, which is next week, basically. So it's something that you need to keep an eye on, especially if you are focusing on how to shift a bit this focus from the research into the policy, into the standardization. And this is where we wanted to give you the 2 cents from the European bioplastic side. We wrote down a position paper on this. It's on our website. You can download it. But I think it's really interesting that this is coming up together now. And there is a meeting at the end of May, beginning of June, that is bringing together this intergovernmental panel for discussing the final text of this treaty. So this is something that is still possible if you have contacts to your policymakers in your countries to give information to them about what you have been doing in terms of bio-based material, bioplastics, sustainable development of new materials. And you can actually feed them in to understand how we can reduce altogether the plastic pollution, and in the end, make our planet last longer for the next generations. So I will pass the slides, but in any case, just it's not up to the single companies to implement, or the single organizations, but to contribute. It's going to be demanded to the national governments, just to be aware, because maybe this was skipping through the news, and this is something that it's very important to remember, just to give you the big framework. I just wanted to wrap up, thank you all for all your participation, the patience, also with the technical downside of this meeting. We made it happen. Thank you, Willem, as well. And we will see you online. So basically in the next few weeks and months, when we will get back to you about the results of these different proceedings and materials. So thank you a lot for contributing to this. In Germany, we just do like this, but you can also clap your hands. It's the same. Yeah. Thank you. Any remark online, or can we close it from here, Estela?
I think that there are many thank yous. Thank you from the chat, but I don't see any question. Lots of applauses and thank you.
Yeah, perfect. So it was a pleasure, and we will make everything available as soon as we can, as soon as we go back home. Good, thanks a lot. Enjoy the coffee break. It's in Dubai, and for you that are at home, stretch your legs and see you next time at the next maybe conference in person. Thanks a lot. Bye-bye.